Today we will discuss about the ripple factor derivation of a half-wave rectifier circuit. So this is a typical half-wave rectifier, and if we apply an input like so, which is Vm sine of theta, then this diode will conduct for the positive half cycle of the input waveform, and we will get the V out to be the same as that of the input waveform, whereas for the negative half cycle, the diode will try to oppose the current because it will try to flow from cathode to anode, and therefore the diode will behave as an open path, and we get the output voltage to be equal to 0 volt. So the output waveform can be drawn like so, where the positive half cycle is replicated for the input waveform with the same amplitude Vm, and the negative half cycle will lead to an output voltage of 0 volts. Now note that although this is a DC signal, but this is an impure DC in the sense that this DC signal will contain some AC components as well. And we have the concept of Fourier series. So if we do the Fourier series of this particular waveform, we will find the DC component as also the sinusoidal components which are forming this waveform. And so it is imperative to know that what is the amount of DC component and what is the amount of AC component, and then find the ratio of the two. So what is the amount of AC component relative to the amount of DC component? Because remember that the objective of a rectifier is to convert AC to DC. So ideally we want that the output waveform should have zero AC components and it should be purely DC. Unfortunately, because this is not a pure DC, we have to come up with a metric which can give us a measure of the amount of RMS component to that of the average component. RMS component is in terms of the AC value, whereas the average value will talk about the DC value for this waveform. So this leads us to the idea of ripple factor, and ripple factor is simply, formulation wise, this is simply equal to Vrms by Vdc whole square minus of 1, and this is within a root. Now note that the basic idea is that over on top of this DC signal, the AC components are present. So the AC components are what that ripple is. So ripple means some sort of a wavy surface or something like that. So your DC signal is impure, and that is represented by this ripple factor value. Ideally, we want that the ripple factor should be equal to 0 for a pure DC signal. Unfortunately, it is not the case, and that is what we will look at in this lecture. So the definition for ripple factor in terms of its formula is given by Vrms by Vdc whole square minus of 1 within the square root. So let's go about trying to find out the expression for Vrms and the expression for Vdc, where the output waveform looks like this. So for Vrms, we know that this talks about the root mean square value. So you have the signal which is present between 0 to pi, because from pi to 2 pi the signal is 0 and it doesn't make sense to write it. So my signal is existing only between 0 to pi, and then the signal value is Vm sine of theta. So for root mean square, we go in the back way. So we first square this signal. This is the squaring of the signal, Vm sine of theta whole square. Then we find the mean of this signal. Mean of this signal means we find the mean over the entire time period, and the entire time period is 2 pi. So 1 by 2 pi integration of 0 to pi Vm sine of theta whole square d theta. So this is the mean and square term, and then you take a root of this entire expression. So this is the root term. So root, mean, and then here is the square term. And then what we can do is Vm square, we can take it out of this integral, and then we know that we cannot directly go ahead with the integration of sine square theta, but we do have an identity which is 1 minus cosine of 2 theta is equal to 2 sine square theta. So if we can make this substitution, then we can go ahead with solving the integral, and therefore we multiply both numerator and denominator with 2, and then make the substitution of 2 sine square theta by 1 minus of cosine 2 theta. And therefore this is the expression after making that substitution. Then we can separate out the terms, and then we find that root under Vm square by 4 pi integration of 0 to pi d theta negative of integration of 0 to pi cosine of 2 theta d theta. And then theta is the integration value for integration of d theta, and the lower limit is 0, upper limit is pi, whereas for cosine of 2 theta the integral turns out to be sine of 2 theta by 2, and again the integral limits are from 0 to pi. So for the first case we have pi minus 0 as shown here, and then for the second one we have sine of 2 pi by 2 minus of sine 0 by 2, and then we know that sine 2 pi is equal to 0, as also sine 0 is 0, and therefore it turns out that this becomes Vm square by 4 pi multiplied by pi within the root, from where we find that the RMS value is equal to Vm by 2. So the RMS value is dependent on the amplitude of the signal, and half of that value is the RMS value. Remember that with the square root, normally what happens is that we in mathematics write this to be plus or minus Vm by 2, but then RMS value cannot be negative. This has to be a positive quantity. So this is the RMS value of our output signal. So let's start with the derivation of the average value or the DC value. And what we find here is that this is simply equal to the area under the curve over the time period. So the time period over here is 1 by 2 pi, and the area of the curve is the integral from 0 to pi of Vm sine theta. So integration of 0 to pi Vm sine theta d theta, and therefore we can take Vm out of this integral, and integration of sine theta is negative of cosine theta, and then we have negative of cosine pi and then cosine 0. So we can remember from our course on trigonometry that with cosine function it starts with 1 and then goes to negative 1 at pi, and then again returns back to positive 1. So at cosine pi its value is negative 1, whereas for cosine 0 it's equal to plus 1. So negative of negative 1 plus 1 is 2, and then 2 and 2 cancels out, and the average value turns out to be Vm by pi. So note that with the RMS value it was Vm by 2, whereas with the average value or DC value this is Vm by pi, and so obviously the DC value is less than the average value, less than the RMS value. So this should be reflected in our ripple factor, and by definition we have the Vrms by Vdc whole square minus of 1 root under, and so we can substitute the value of Vrms, which is equal to Vm by 2, and we can substitute the value of Vdc, which is equal to Vm by pi, and then carry out this calculation, and the ripple factor comes out to be 1.211. So this is the ripple factor for a half wave rectifier. Recall that the ripple factor of a rectifier, a rectifier that provides a pure DC output, should be equal to 0. There should not be any ripple component present in our output. But because the output of a half wave rectifier, it's an impure DC, therefore there is substantial amount of ripple present, so much so that the Vrms value is much more as compared to the VDC value, and therefore we end up with a ripple factor of 1.211. So next, when we will proceed to the full wave rectifier, you will find that the ripple factor will substantially decrease. For a full wave rectifier, it will turn out to be 0.48.